In this video we're going to learn how to do maxes and mins. It's a calculus thing that we use in physics for energy, especially potential energy, to find where there's a stable and unstable equilibrium. But let's just kind of concentrate on the basis of the calculus, and this is my way of understanding maxes and mins using something we already know to know something that we don't know. So first of all, you notice I have this grid here. Let me move this over to the side. And you should already know that if theta is taken from the x-axis, then this right here, this right here would be the y component, obviously, and this right here would be the x component. Let's just do it that way. It'd be a little easier to see. Now, if as theta increases, you should see that y increases. You should also see, you should be able to see when theta equals 90 degrees, theta equals 180 degrees, and theta equals 270 degrees. So let's write down a few things that we have here. So this is going to be theta, then I'm going to have sine of theta and cosine of theta. Make our nice little grid here so that we can graph this in a little bit. I guess I don't need that much space. Okay, so at 0 degrees, we see that at 0 degrees there is no y component. This would be theta equals 0 degrees. So there's no y component, and 100% of that vector, if we just call this our vector r or something, if it's at 0 degrees, then 100% of it is along the x-axis. Well, at 90 degrees, cosine is 100%, sine is 100%, and cosine is 0%. At 180 degrees, then the sine is 0 and cosine is negative 1. At 270 degrees, cosine is negative 1, sine is negative 1 and cosine is 0. And then we could get back to 360, just expand that a little bit more, and that gets us back to 0 and 1. Now I'm going to need this grid, so let me bring it over to where we're working. And let's take those numbers that we just found. So we're going to call this sine theta. And we get sine of theta, it starts at 0. We'll call this 90 degrees, 180, 270, 360. Starts at 0, then it goes positive, 0, negative, 0, which gives us a classic sine curve. Now, notice that cosine starts at 1, then it goes to 0, negative 1, 0, etc. Now you'll notice, you see right here, the slope of this line is a positive number. This is a positive number. The slope here is 0. This value here is 0. The slope is negative, negative, 0, 0. So it turns out that to go from here to here, you take the derivative, which is slope. So cosine is the first derivative of sine. So this is our function. Well, I guess I'll do it this way. This is our function, and in this case I'm just going to call it f. This is going to be f prime, and guess what? We're going to have f double prime. So now let's look at this. Well, this has a slope of 0, 0, negative, negative, 0, positive, 0. And it shows here that if we take the second derivative, which is again the slope, we get a negative sine of theta. Okay? Now let's remove this, and we'll move over. Now let's look at some very interesting things here. if we wanted to find the maximums, this is a max and this is a min. So 4 maximums and mins. These are points where slope equals 0, or the first derivative equals 0. Notice the first derivative here is 0. Derivative is 0. Well then, now let's look at this. Now that once we know that the first derivative is 0, on the second derivative, I'm just going to type this a little bit easier. A maximum, I'll make this bigger so we can see it better. A maximum on the function, call it f, is a point where the first derivative, f prime, equals 0, and the second derivative, f double prime, is negative. So let's look at it. So I'm going to circle maximum, max, max. Notice that this is 0 for the first derivative and a negative for the second derivative. Well, then we can do this again for a minimum. A minimum for f is where f prime equals 0 and f double prime equals a positive. It's that simple. Okay, so I'll go ahead and box that. Minimum, minimum, minimum. So this gives us our procedure for finding a max or a min, which is, move those out of the way. To find maxes and mins. 1. Take first derivative of the function, set it equal to 0. Solve for these points. You're actually going to need the numbers. 2. Take second derivative and evaluate at the points you found okay. Now I'm looking like I'm running out a little bit of space here, so let me go ahead and try to save us a little bit of space here. I guess I'm going to have to move this. I may or may not have to find more space here. Okay. Yeah, I can just move these out of the way. I know that's not completely out of your way, but it's completely out of mine. So I have a function here. Well, actually, we can just do it right here. We're going to use this space, and I can get rid of this. Here's our function. F equals this. I guess I should really say f of x. Alright, well, where are maxes and minimums? Step 1, and let's go back and forth and look. Our maximums and minimums are points where the slope equals 0 because they're turnarounds. At the maximum point, you're about to turn around. At the minimum, you're about to turn around. So step 1, take the first derivative and set it equal to 0, solve. So f prime, first derivative, equals, multiplied by the power, multiplied by the power, set this equal to 0. Okay, well now you should remember how to do this, but let's just make sure. I can obviously factor out a 3, and that gives me 2x minus x squared equals 0. I can take an x out of that. Now, to say that these two equal 0, it means either this equals 0 or this equals 0, so we set them equal to 0. That one's equal to 0. Or 2 minus x equals 0, so x equals 2. These are our 2 points where the slope of the first derivative, the slope of the parent function, equals 0. Now, the next step, now that we know where our maxes and mins are, we have to know if they're maximums or minimums. We have to know if at this point they're negative or positive. So we take the second derivative. And again, I'm taking the derivative of this function. This was the first derivative. This is the second derivative. That will equal 6 minus 6x. Now I'm going to put in 0. So f double prime of 0 equals 6 minus 0 equals 6. Therefore, f double prime of x is positive, so f must be a min at this point. Okay, let's look once again. We found a positive point, which means it must be a minimum. So let's evaluate. F double prime of 2 equals 6 minus 12 equals negative 6. Therefore, f at 2 is a maximum. Wait a second. Is a maximum. Okay. Now, you may say, did we get this right or didn't we? We think, okay, our evaluation is that at x equals 0, this is right here. That must be a minimum. Or, as we say, concave up. It's in a valley. At x equals 2, we have a maximum, which is concave down. We have a hill. Well, I graphed this in Excel earlier. Let's take a look. Boom. There you are. At 0, we have a hill, a minimum, and at x equal 2, we have a maximum. 2 is a maximum, exactly as the calculus showed us, and at 0, it's a minimum, exactly as calculus had shown us. Once again, to recap. Cosine is the derivative of sine. Negative sine is the derivative of cosine. You'll notice that a maximum for the parent function is where its slope equals 0 for the first derivative, which is a negative value on the second derivative. A minimum is where the first derivative is 0 and the second derivative is a positive. Now, there's of course one other way of doing it. Well, there's a couple other ways of doing this, but an easy way of doing this right that we could also have done is take x equals 0 and x equal 2, and we could put them up into the parent function. And if we place these up in the parent function, we get f of 0 equals 0. And that doesn't seem to teach us much, but if we put f of 2 is going to be 3 times 2 squared is 4 minus 8. That equals 12 minus 8, which is 4. This means that this point is at, this one is at 0, 0. This one is at 2 and 4. Well, this is higher than that one, so this should be a minimum, this should be a maximum. I don't love it as much as using the calculus, but that's another possibility.